Hello, Professor Simmons here. Today we're going to talk about surface area. We're going to think about how we could find the area of a curved surface that's rippling along above the xy plane. And this will be somewhat an analogy with finding the length of a curve, just a curving line that we discussed in a previous video. So let's think about a curved surface defined by a function f of x and y that's equal to the z height of the surface above the xy plane. So we've sketched here the area of a small patch of our curving surface dA, and that patch of area is perpendicular to direction that we'll call n hat. Similarly, we have a little standard dx by dy patch of area on the xy plane, which is naturally perpendicular to the direction z hat. And here we see that if we project our patch of curved surface dA down onto the standard patch dx dy, the angle between the two patches of area is simply the angle between n hat and z hat, and we can call that gamma. And literally, that's the projection angle in the sense that dA multiplied by cosine gamma equals the standard little area patch below, dx by dy. And this makes sense if we think about it. If the upper patch were parallel to the xy plane, the two patches would be the same size. But the more steeply we angle the upper patch with respect to the xy plane, the larger that upper patch actually is compared to the standard size patch below. So the surface area that we're trying to integrate overall for the upper curved surface is just adding up the little patches dA, which is adding up dx dy over cosine gamma for each little patch dA. In order to do the calculation then, we need to find gamma. We'll do it by pinning down the direction n hat in a convenient way. Since z, the height of the surface above the xy plane, is described by this function f of x and y, we could define a new function phi that is z minus f of x and y. By definition, phi would always equal 0. That means that our function phi is actually constant. But for a surface that is described by a constant scalar function, the gradient of that function is always perpendicular to the direction of that surface phi at any point, as the book kindly reminds us. So that means we know that the direction n hat, since it's perpendicular to the surface, is precisely in the direction of the gradient of phi. That is, it's in the direction d phi by dx x hat plus d phi by dy y hat plus d phi by dz z hat. Knowing that, as we'll see on the next page, we can actually calculate cosine gamma and do our area integral. So here we are. Let's compute gamma. We've just said that gamma is the angle between n hat and z hat, but we've remarked that n hat is in the direction of the gradient of phi, and the dot product then between the gradient of phi and the z hat unit vector is just the magnitude of gradient phi times the magnitude of z hat, otherwise known as 1, times cosine gamma by definition of the dot product. So this is great. We just need to figure out these other factors in the equation, and that will leave us with cosine gamma. So we noted z hat, by definition, is a unit vector with length 1. The dot product over here between gradient phi and z hat is, by inspection, just the partial of phi with respect to z, since that's the z component of the gradient of phi. But our definition of phi was z minus f of x and y. The partial derivative of that with respect to z is simply 1. That's great. We're getting lots of simple answers. The only thing we have left to calculate then is the magnitude of the gradient of phi. Well, the square of that is simply the square of d phi dx plus the square of d phi dy plus the square of d phi dz. We remember what phi is. We can take those derivatives, and here is the result. So we find then that cosine gamma is simply d phi by dz divided by the magnitude of the gradient of phi from everything we said above, and that's simply this ratio. But that looks really familiar, and in fact it leads us to say that the surface area then is adding up the areas of these patches, which is the integral over dx and dy of not cosine gamma but secant gamma, which brings the square root into the numerator, where we see it's an exact generalization of the one-dimensional case. So literally, for a function f of x and y defining the height of a curving surface above the xy plane, this is how you calculate the area of that curving surface.